Okay, so this is lecture 1 in Calculus 2. In this lecture, we'll cover, or not cover, we'll introduce the natural logarithm. So this is section 5.1. The natural logarithmic function. In particular, with relation to differentiation. Okay, so if you recall from Calculus 1, there is this general power rule for integration. It looks something like this. So recall that if we have the indefinite integral of x to the power n dx, then this is going to be x to the power n plus 1 all over n plus 1 plus your integration constant c whenever n is not equal to -1. Now this right there should be of concern, right? Because when n is -1, so what would that look like? So what about the indefinite integral of x to the power -1, which is the same thing as saying so this general power rule applies in every case except for this. But this is fairly simple, right? Like we know what this function looks like, and we know what 1 over x looks like. And we know that the definite integral measures area under a curve. This curve is fairly simple. We should be able to somehow define this, right? And that's exactly what we're going to do. We're going to get to a place in this lecture where we will know how to evaluate this. In order to do that, we need to introduce a definition. Okay, so, and this definition is defining the natural logarithm. So, the natural logarithm, I'll just say the natural logarithmic function is defined by the following function. So ln of x is equal to the definite integral from 1 to x of 1 over t dt provided x is greater than 0. Okay. So in calculus, this is how we define the natural logarithmic function. This is different than how you would have seen it in maybe a pre-calculus class or an algebra class where you have bases and things like this. In calculus, we have the machinery to define the natural logarithmic function in terms of an integral, a definite integral. Okay. So what is this measuring, right? Like, so you give me an x greater than 0, we plug it in here, we evaluate this integral. What is this measuring? Well, it's measuring the area under the curve of that function, 1 over t. So what does 1 over t look like? Well, if you were to plot 1 over t, or graph it, it would look like that, right? And this definite integral is calculating the area under this curve on a given interval, 1 to x, right? So maybe 1 is like right here. So if you chose x to be maybe there, then this would evaluate that area. Can y'all see that? Yeah, just a little bit. If you chose x here, like to the left of 1, less than 1, then it would be that area there. Yeah. So, okay, from this definition, we can just immediately observe a few things. So first off, so these are just like little points to make about this definition, is that if x is greater than 1, then this is going to be a positive value. So if x is greater than 1, then the natural log is positive. If x is less than 1, then we use our rules of integration, which you're going to have to review these things from Calculus 1 if it's been a little while. If x is less than 1, but greater than 0, then the natural logarithmic function is going to be negative. So 0 less than x less than 1, then natural logarithmic function is less than 0. It's negative. What else can we learn about this definition? Just by looking at the picture, really. Well, if we take x larger and larger, right? Like, so here's my first x that I pick. If I pick another, like x plus 1 right there, then we integrate and have all that area. If I pick x plus 2, we see that we're getting more and more area, right? We see that the function is increasing. So the next point to note is that the natural logarithmic function is strictly increasing. Right? Hopefully that makes sense. You see that if you pick larger and larger x, you're just getting more and more area under the curve, so that function is increasing. Okay. Now, there is a theorem that you probably don't remember from Calculus 1. It's another variation of the fundamental theorem of calculus. In the textbook, it's called Theorem 411. So I'm just going to recall that real fast. And I'm mentioning this theorem because it's going to give us some valuable information about this function. So recall Theorem 411. Okay. Which states that if f is continuous on a closed interval containing the number a, then the derivative with respect to x of the definite integral from a to x of f of t dt is equal to f of x. So this is another way of stating the fundamental theorem of calculus that you would see in a Calculus 1 course. We have definite integral from a to x. X is the variable here. If we take the derivative of this with respect to x, we get the function evaluated at x. So here we have something very similar, right? We have a definite integral from 1 to x of a function of t here, right? So what this is going to say, what this implies, is that dx of this natural logarithmic function is a derivative of this thing, right? And if we apply this theorem here, hopefully you can still see, if we apply this theorem, we see that the derivative of this is going to be one over x. So this is like another point to make about this definition. Dx of the natural log 1 over x. Okay. So more generally though, like if we have a function of x that's in place of x here, then we can apply this chain rule and get a more general theorem. So let me just go ahead and write that down while we're here. So if u is a differentiable function of x, then dx of the natural log of u is equal to the derivative of the outside times the derivative of the inside. This is this chain rule, right? The derivative of the outside is just 1 over u times the derivative of the inside. We don't know what that is, so we just write du dx. So this, that, there, and there. Just based off of this definition, we have 1, 2, 3, 4, 5 facts to work with about how this function behaves. And if you recall from like a Calculus 1 course, calculus is the study of change and how things change, and the analysis really of how functions behave. So as soon as we have this definition, we're going to want to perform some type of analysis like we just did to kind of understand the behavior of this function. And this is going to repeat itself over and over again in Calculus 2. We're going to introduce a definition of some function, and then we're going to apply what we've done previously to understand how this new thing behaves. And that's sort of, oh, I need to be very careful here. U better be greater than 0. I almost forgot. X greater than 0. Because that's the only time that function is actually defined. So on a very deep level, those of you majoring in math would want to do this a lot, to think about this a lot, to play with this function a lot. On a sort of higher level, a more practical level, you're just going to want to know how to differentiate and integrate these things, i.e. this star right here. And that's what we'll do now. So let's go ahead and differentiate some functions that are defined in terms of the natural log, which means we're really just going to use this fact over and over again, though it's important to really know all of these. Okay. Some examples. We'll start simple. Let's look at the derivative of the natural logarithm function composed with 2x. Okay. Now take a moment to apply that rule, which is really a theorem, to this problem. So take a moment to do that. I'll pause the recording. Okay, so let's go ahead and break down this simple problem as much as we can. So this is not natural log of x, this is natural log of 2x, right? So in this problem, you can think of, well, u could equal 2x in this problem. Right? This is a function of x, right? U is a function of x. It's a differentiable function of x, which means that it's subject to this bullet here. So we should go ahead and differentiate this and see what it is. So du dx is just equal to what? 2, right? So then we just plug in. This is going to be 1 over u, which is that, times du dx. Oh. It's just going to be 1 over x. Hopefully all of you can read. Yeah. Okay. So let's do a little bit more complicated example. Not much more, but slightly more complicated. Let's look at the derivative with respect to x of the natural log of x squared plus 1. And I'll go ahead and pause the video here as well. Okay, so here you can treat u, or not treat, you can just let u equal x squared plus 1, right? So now here u is a differentiable function of x. So then du dx is 2x, right? So now this derivative is 1 over u times du dx. So altogether, it's going to be 2x over x squared plus 1. Okay, so Luis, you got it. Okay. All right, so let's do another one. What about the derivative with respect to x of x times the natural log of x? All right, take a few moments to try that one. Okay, so here, you just have to apply the product rule. So maybe I'll write it here. So recall that the derivative with respect to x of f of x times g of x. This is going to be f prime of x times g of x plus f of x times g prime of x. So this is the product rule. Okay. So here we have two functions. We have the function y equals x, and we have the function y equals natural log x. So we're taking the derivative of this product, so we apply the product rule. So what is this going to be? This is going to be derivative of the first thing, so derivative of x is just 1 times natural log of x plus x times the derivative of the natural log. And this becomes natural log of x plus 1. Okay. Okay, let's do another one. Yeah, one more. Find the derivative of the natural log of x all cubed. Okay, so again, a lot of this is just recalling this bullet point together with the fundamental theorems from Calculus 1. Okay, so as was just brought up, it is an application of the chain rule, right? We have a composite function, so this function composed with that function. So this will be the derivative of the outside function is going to be 3 natural log of x all squared times the derivative of the inside, which is whatever x. So altogether, 3 natural log of x squared over x. Okay, so that would be the answer there. Okay, so these were just applying what we derived from the definition using the fundamental theorem of calculus that I wrote down earlier, just applying this bullet point to find the derivative of functions involving the natural logarithmic function. So now that we kind of understand the mechanics of taking these derivatives, we probably need to study the function a little bit more. In particular, what is the natural log of 1? Right, so, well, if we reference back to the definition, this is the definite integral from 1 to x, but x in this case is 1. 1 over t dt. What is the definite integral with where the limits of integration are the same? What does this evaluate to? Like any function, any integral function, if you have the definite integral from like a to a, f of x dx, what does that evaluate to? How much area is under that curve? Forget this for now. This is important. How much area is under the curve of f from a to a? Like,
some people in the chat are saying like either 0 or none, since it's just that one interval. You're not really measuring any space in between.
good. It's 0. There's no area defined there. Okay, so that's an important fact of natural log. In general, if you have the same limits of integration, your integral is going to evaluate to 0. So that's an important fact about the natural logarithm. If you plug in 1, you get 0, and that's because, by definition, when you evaluate that definite integral, you have 0 area, 0. Okay. Some other important points. Natural log of a times b is equal to the natural log of a plus the natural log of b. And the natural log of a to the power n is equal to n times the natural log of a. These two bullet points will derive next lecture. Just take them as facts for now. Okay. And if you're curious, I would highly recommend, especially for the math majors, to see if you can justify why these would be true based off of the definition. Okay. So how can these rules be useful? So, another example, find the derivative of the function f of x equals to natural log of x times x squared plus 1 all squared all over the square root of 2x cubed minus 1. All right, I'm going to pause it and let you try. All right. So the way that I would do this is I would definitely expand this as much as I can first, using that or that or that. And then after it's expanded as much as I can, then I take the derivative. Okay. So immediately I see that this function, before taking into any derivative, is equal to this. The natural log of a quotient, right, of a ratio, is the difference of the natural logs. And this rule, the product rule, implies the quotient rule. So that goes there. Okay. Now, once I'm here, I see that I have a product in there, right? That times that. And then I also see I have a power here. It's like being raised to the 1/2 power. So that plus natural log of this thing minus natural log of this. Make sure you can read that. So now I can use this exponent rule for natural logs, bring the exponents down. Okay, so that function f, if I expand it out, really looks like that. Now that it looks, I can't do anything else. Now I'm going to take the derivative. So f prime, derivative of that, plus derivative of that, plus derivative of that. So this one's easy. 1 over x for that one. And then 2 times derivative of this. We did this earlier, right? We did the derivative of natural log of x squared plus 1. So 2 times the derivative of that over that, basically. So x all over x squared plus 1 minus 1/2. So the derivative of this over this. So what is that going to be? 3 times the 2, so it'd be 6x squared all over 2x cubed minus 1. Hopefully you can read that. Okay, so if I simplify this out, so it'll be 4x there. Minus, that half can divide out the 6 and make it a 3. So 3x squared all over 2x cubed minus 1. And for all, that's the answer. Like, I'm not going to combine that. You could combine like terms, which might give an answer close to what Gregory said, honestly. But I'm too lazy to combine that. I don't want to do it. That's the answer. Okay. So this is an important thing to know. Combining these rules first to simplify a messy expression into easier bits to deal with, and then differentiating those bits one at a time can make life a little bit easier when dealing with these kinds of things. Okay. Oh. Let's look at another problem now. Find the derivative of y equals to, say, x minus 2 all squared over square root x squared plus 1 x not equal to 2. Okay. So notice anything different about this question, this example? There's no logarithms, right? All the derivatives we've been looking at so far have had natural logarithms. I don't see any here. Well, this is a problem where it can be beneficial to introduce logarithms. Okay, so notice, I'm confident that all of us would be able to take the derivative of this if we were very careful, right? We have like a quotient, we have a power there, we have another power down there. There's this messy quotient derivative formula. We could do it, right? But because we know that equations hold as long as you perform the same operations to both sides of the equation and avoid division by zero, maybe we can take the natural logarithm on both sides of that equation and look at it in a different way. First, though, we have to verify that that's okay to do. So if I take the natural logarithm on both sides, does it make sense? That's my first question to ask. Okay, so this is actually an important condition here. Because the natural logarithm is only defined when the argument you give it is greater than 0. If x were to be equal to 2, it would be equal to 0, right? And you can't evaluate the natural logarithm at 0. So this condition is actually important. Also, whatever you evaluate the natural logarithm at, the argument needs to be positive. Since you're squaring this term, that's positive. That term is being squared, that's positive. So it's going to be non-negative, right? So we can take the natural logarithm on both sides because this is always non-zero because of that, and it's always greater than 0 because you're squaring the terms. So we're allowed to take the natural log on both sides. But how did this help us? Well, it helps us because now we can apply the rules to expand natural logarithms to make this less messy. So what do we get? We get that natural log of y is equal to the natural log x minus t all squared minus natural log of x squared plus 1 all raised to the power of 1/2 is the square root. Then we can use this exponent rule to bring down the exponents. And now it looks a little bit nicer to me. I personally hate using, or not hate, I just forget the quotient rule all the time that you could use to find the derivative of that. This is easier for me, okay? So now, if we want to find the derivative of y, we can use implicit differentiation maybe. We can take the derivative on both sides, right? So yes, let's go ahead and do that. Using the excellent Leibniz notation. I love this notation. Just to illustrate that we're taking the derivative on both sides. And now how is this, what's going to happen? Okay, on the left-hand side, we have the derivative of natural log of y, where y is a non-negative function of x. So we just apply the rule. This will be 1 over y times dy dx, right? And that's what we're searching for, right? We're trying to find dy dx, and I see it right there. And then on this side, we get 2 times 1 over x minus 2 times derivative inside, so it'd be 2 over x minus 2 minus 1/2 times the derivative of this, so it'd be x1, and then the derivative of the inside is x. Those 2's divide out. We get 1 over y dy dx is equal to 2 over x minus 2 minus x over x plus 1. But again, we're searching for the derivative, and we're using implicit differentiation. We just multiply both sides by y, and then we finally get that dy dx is equal to y times all this stuff. Okay. So that's it. Now, up until this point, we've just been going through the mechanics of it, right? I wrote down a theorem. I said this theorem implied this other theorem. I wrote down some rules that were implied by the definition. And then we just started differentiating a bunch of stuff. But why are we doing this? Right? Like, I think this is a notion that is often overlooked when you're in calculus and you're trying to remember all the rules and to keep track of the algebra and like keep your bookkeeping down with like your steps. Like, it's often lost why you're doing the thing that you're doing. Why do we care about derivatives? Can someone give me an answer? Like, why do we care about derivatives? I'm looking. Somebody. Anybody?
Because it's calculus.
We just spent basically 45 minutes calculating derivatives. Why are we doing it? Like, now in an ideal world, this would be hammered into you in a Calculus 1 course, but that's probably not the case. Anyone else want to take a guess at why we want to care about derivatives?
In all seriousness, though, I guess it would be because the derivatives are technically the base for everything. Eventually, we start solving the integrals, and then that comes into play, and just the derivatives intertwine to everything when it comes to calculus.
Right. They do. Derivatives are basically half of calculus. That's one way of looking at it. But like, so computer science majors, chemistry majors, one math major, geology majors, why do you care? Like, why do you want to know what a derivative, like, why would you ever want to calculate one? We don't know, right? Like, it's okay if you don't know. A lot of it's not so clear to you. It's not obvious why derivatives would be important. So, okay, let's go to like the very fundamentals. This is almost like we're taking a slight step back to Cal 1 right now to kind of re-emphasize why derivatives are important. Actually, I'll do it over here. And I was going to ask another question involving logarithms, but before I get there, I have to re-emphasize this importance. So I apologize for the sidetrack. There's a curve. Some continuous function or smooth function f. And suppose here's c, some number c. How do we calculate the slope of this line? What's the slope of that blue line?
One.
It could be 3, but like in general, if we have a function f in a number c, some defined in some open interval that f is defined on, how would we find the slope of that line there? What's that line
This
called?
is the
What?
is it the first derivative of that line at that point?
This line has slope equal to f prime of c. The derivative of that function evaluated at c gives you that slope. So at a very, very like base level, you could say derivatives are important because they tell you the slope of the line tangent to the curve at a given point. That's one thing you could say. It's not very much, but it's something, right? Why do we care? Why would we care about slopes? Oh, velocity. Someone said velocity. I got a tangent line from Gregory. Zachary said to get the slope at a point. Okay, so velocity is defined as the first derivative of the function of position, right? Velocity is very important for physicists, geologists, chemists, and basically rate of change. That's what velocity is. It's a measure of rate of change. And the slope at a given point, the slope of a tangent line to a function at a given point is telling you the rate of change at that point, the instantaneous rate of change. As nonsensical as that phrase means, that phrase sounds, instantaneous rate of change, doesn't make sense. But that's the terminology that we like to use when describing these things. So there's a lot of computer science majors in this course. Why would a computer science major be interested in knowing how to find these slopes? Any wild guesses? So, okay. Say yes or no in the chat. How many of you have heard of machine learning? Oh, I got one person. So, someone's heard of machine learning. Have anyone else heard of machine learning? Get a no, no, yes, no, yes. Briefly. So, because like I spend a lot of time working in data science, I'm going to go ahead and go that route. There are two different routes I was going to consider going. There's a physics type of route to explain why this is important, why derivatives, why should we care? But then there's also this other machine learning data science way that I'm gonna use. So for those of you that don't know, machine learning is it's a subfield of computer science, mathematics, and statistics. It's like an intersection of all of them. It deals with writing computer programs to take in data and learn from that data on their own. So instead of like pre-programming in like if, else, if, blah, blah, blah programs, you write algorithms that use the data to learn how to get better, right? So for example, how does like all of you have smartphones that can take a picture of a check and then it like can deposit the check for you, right? Well, how does it know what the digits are on the check that you deposit, right? How does this image tell it that, right? Well, basically, and I swear I'm going somewhere with this, with relation to derivatives. Suppose you have a function which takes as input weights, and it outputs based off of like taking those weights and like, well, suppose you have input a picture. The picture is converted to like a bunch of numbers and you multiply it by some weights and it spits out whether it's a 1, a 0, a 2, a 4, whatever, a digit, right? And this function is then fed into another function, okay? It's getting more complicated, but bear with me. That this new function that we've made, if you put in a picture of a 1 and it spits out a 9, that's bad. If you put in a picture of a 9 and it spits out a 9, that's good. So for each input image that you put into this function, the better it does, the lower its cost is. The worse it is, the higher the cost is. So you can imagine like a function where the top means that it's doing bad and the bottoms mean that the function's doing better, right? So how do you find the bottoms of functions? Well, that's a bottom, a relative bottom of that function, right? If you have some function that's behaving like that, right? There's a bottom, there's a bottom. If you can find those bottoms and learn how to get there, you can get your function to do better. Right? Like if the higher you are is bad, the lower you are is good, you want to find these bottoms. In Calculus 1, these are called local extrema. Does anyone remember local extrema from Calculus 1?
Yes, sir.
These are local extrema too. These peaks, right? But in machine learning, you typically want to find local minimums because the minimums correspond to a cost function that you want to minimize. Minimum. How do you find local extrema? Does anyone remember? So one answer to this question, you could say local extrema. So how do you find those things? I see critical points. Good terminology. So basically, you want to know when the derivative is equal to 0 or the derivative doesn't exist. Okay? Do you want to do like a concrete example to like reinforce this notion? Say check if you want to do one. I'll walk you through each step of this.
Okay, sure.
Okay. Trust me, geologists and chemists and mathematicians in the audience, you should be wary of machine learning as well. This is not just for the CS majors. A lot of geologists use machine learning techniques to predict where new wells might be without having to send really expensive probes out to do that. In chemistry, machine learning is leading to the prediction of new molecules to help with the manufacturing of medicines. And like even the COVID vaccine was sped up by machine learning techniques. And the math majors in the class, if you ever want to make a lot of money, knowing more about machine learning is good. Okay. All right, guys, let's, I'm going to stop this recording because this is branching off a little bit too far from the logarithmic functions. So I'm going to split the recording into 2 recordings.